Hey kids, Smath here. So here's our second video on rates. And what we're talking about today is rate laws and how to calculate rate laws. And so what is a rate law exactly? What it is it's something that shows us, rate laws are going to show the relationship between the speed and the concentration of the reaction. These are also known as differential rate laws. Now, we take AP, you further your study in chemistry, we talk about this later. There are also things called integrated rate laws, which don't depend on concentration, but depend on time. We're just going to deal with differential rate laws. This is how does changing the concentration make a reaction go quicker? And so what we have is this thing called rate, a rate law expression. This is where rate is equal to K, A to the X. Now, A is the concentration. That's the molarity that we're dealing with. And X is called the reaction order. That X has to be calculated experimentally. Now, what about this K? This is a lowercase k, this K right here, and that's called the rate constant. And he's a pretty important player in this equation because simply put is the larger the K, the faster the reaction. The lower the K, the slower the reaction. Okay, now this has to be done experimentally. And so we're going to do some calculations here. So right now I've got NO2, and NO2 breaks apart. I lost some of my formatting here, so bear with me. We're going to find the reaction order, and that rate's going to be the rate law expression, rate equals K, NO2 to the N. That N does not equal the coefficient. That can't happen. All right, it's not just equal to whatever's in front of it. That's the rate law expression. N is called the order of the reaction. And the reason that's important is the larger that value of N, the more importance it plays in speeding up a reaction. So if N was equal to 1, that'd be nice. It would speed up the reaction. But if N was equal to 2 or 3, that's going to have twice an effect or 3 times an effect of speeding up the reaction. Okay, that's the rate order. And that's what we're going to be calculating from the data that we're given in the problems. Okay, so this is a rate law. Notice we're not going to include NO or O2. Those aren't going to come into play. That would be pretty weird. Well, how come the speed of the reaction doesn't depend on those? Because they're products. The speed of the reaction doesn't depend on the product. That would be like saying, hey, if I took a sample of gasoline and I lit it on fire, would the speed of that reaction depend on how much H2O and CO2 there is? In a closed system, it might a little bit, but in an open system where we're running a reaction, no. Reaction rates only depend on the reactants. So in this case, that's why we're only worried about the NO2 going on here. All right, so now we look at these rate laws. These are formulas used to determine the amount of reaction per time. So this is a setup for the rate would be the rate Ka, not times. That was one of my formattings that I lost. Excuse me. Get rid of this. Get rid of that. Get rid of that. Can I erase that even? Oh gosh, that would be really nice. Yeah, it won't let me erase that. But this is a multiplied sign here, not an addition sign. So this should be times. So our rate would actually look like rate equals K concentration A to some N concentration B to some M. This A and this A are not related. This B and this B are not related. There is no relationship between the coefficients and the reaction order. Okay? So we're going to skip over that one step and get right here to get to the points math. What are we doing? Teach us how to do the problem. So here's an example I've got set up for you. This is a differential rate of some A plus B equals AB. And here's our concentrations. These concentrations are given to us in molarity, and the rate. This table has to be provided for you. You can't do this. All right. Then it says, determine the rate law and calculate the value of the rate constant. So I'm grabbing my calculator here. Now to get the rate law, it's going to be real easy. What we need to do is look at the data and find a place where A is going to double and B was held constant. So in this case, A doubled from 1 to 3. Now I just erased, I had it written from 2 to 3, but I can't do 2 to 3. 2 to 3, I have A doubling and B doubling, or B getting cut in half. That's not going to work. We don't know. What I'm trying to find is a place where A is changing and A is the only variable that's changing, because now I can show causality that any effect on the rate is due to A, since B was held constant. B is our control. And so A went by a factor of 2 and our rate went up by a factor of 4. Now kids, I'm going to say this really quietly and, don't freak out, but this is a logarithm. Yeah. This is why you learned logs. Now we're going to keep it real simple. We're not going to get too complicated here, but really what we're saying is the change in concentration, 2 to the x equals 4, x equals 2. What we're saying is the change in concentration to x equals the change in rate. That's all we're calculating here. Now let's look at B. We've got to find one where B is constant, or excuse me, where A is constant. A is constant right here, and B doubled. B doubled, the rate doubled. So now let's do that logarithm thing again. 2 to the y equals 2. Well, y is going to equal 1. So now what is our rate law? Our rate law is going to be rate equals K concentration, A to the second, B to the first, and that's the rate law. We're halfway done. That is called the rate law. So what this tells me is if I want to speed up this reaction, change my concentration of A. That's going to make it go faster. Okay, now we got to do the second part where it says calculate the value of K. All right, so the value of K, I can pick any one of these lines. What these lines represent, this is trial 1, trial 2, trial 3. What these lines represent is basically we did this experiment 3 times. Okay. I can pick any line, I still should get the same. So I'm going to plug it in. I'm just going to pick my first line. So the rate, so I'm going to take my rate law. Rate equals K, concentration of A, squared, B, and the rate for the first trial was 0.002 equals K. The concentration of A was 2 squared, and the concentration of B was 1. And now if I solve this, I should say 0.002 divided by 4 gives me a K value of 0.005. That's not a very big number. Guess what? This reaction is going to go relatively slowly. It's not going to go quick. What are we looking for a value of K? Anything bigger than 1 will start to move pretty quickly. So this is a differential rate law. Very simple, A's and B's. Let's do another one with a little more complicated numbers going on here. Okay, so now I have this reaction. I have a bromate ion with bromine and acid, and I'm going to make some Br2 and some H2O. All right, we don't need to understand the chemistry behind it right now. We just need to look using this data. What can we do? So the general form is BrO3 to the N, to the M, and to the P. All right, so we need our data for that. And here's our data. So what we're looking for is 2 trials. Remember, these are just trials. This was trial 1, trial 2, trial 2, trial 3, trial. We had 4 trials. So what I want is to compare for BrO3. I want to compare trials 1 and 2. How come? Because Br minus and H plus both were held constant. Now be careful with these because this gets kind of weird because of the coefficients, or not the coefficients, but because of the exponents. So what happened to BrO3? It doubled. What happened to the rate? It doubled. Wait a minute, it went from 8 to 1.6. No, it didn't. It went from 8 to 16. It doubled. Trust me, do it on your calculator. Divide 1/6, 10 to the negative 3, divided by 8, 10 to the negative 4. You're going to get 2. I got this. Okay, now let's pick our other 2 trials. For Br minus, it looks like it's going to be trials 2 and 3. And we'll switch to a different color here so we can keep him straight. That goes from 10 to 20, where the BrO3 was held constant at 20 and the H plus was held constant at 10. And now this went from 1/6 to 3/2. Also a double and a double. So right now everybody is first order. And now in our third one, now we need to find what looks like trials 1 and 4. The bromine is constant, the bromate is constant, and that went up, that doubled. We doubled our concentration, and look what happened over here to the rate on the right side. It went up by a factor of 4. So what's our rate law? Simply put, rate is going to equal K concentration BrO3 to the first, Br minus to the first. I'm not going to write those exponents. They're ones and they're implied. But the H plus is the important part here, to the second. That's the rate law. And it wants to know what's the constant value. So let's pick a line. I'm going to pick the first line because it's got a lot of ones in it. We like that a lot. And so the rate was 8.0, 10 to the minus 4th equals K, 0.10, 0.10, 0.10 squared. Plug this into my calculator here and go 0.10 squared times 0.10 times 0.10 gives me a small number, and go 8e negative 4 divided by that. Boom. K is 8. That's above 1. This is going to be a fast reaction. This is going to occur. And if we want it to go faster, what are we going to do to make it go faster? We're going to add more H plus, because H plus was the one that had the highest reaction order. The way we would say this is, this reaction is second order with respect to H plus, first order with respect to Br, first order with respect to BrO3, and it's going to be fourth order overall. I'm Smath. This is how you do rate law calculations. I hope this video helped you.